On the 29th of October, an object of interstellar origin, cataloged as 3I Atlas, and only the third of its kind ever confirmed to have entered our solar system, made its closest approach to the Sun. At that moment, it was traveling at an almost incomprehensible velocity of 68 kilometers per second. This event, known as Perihelion, became a focal point for scientists and the public alike, representing a critical juncture that could redefine our understanding of this cosmic traveler. If there was any truth to the swirling online narratives suggesting that this moment could unveil a hidden nature, this was the instant that would test whether 3I Atlas was merely a primordial rock cast out from another star system or something engineered with a far more deliberate purpose. While a significant portion of the digital panic surrounding the object has been systematically debunked by actual tracking data, confirming no unexpected engine ignitions or a direct trajectory toward Earth, the scientific community remained intensely focused. As researchers scrutinized imagery from satellites like GOES-19 and prepared for this pivotal solar pass, they were aware that a single, well-timed maneuver at perihelion could fundamentally alter history. Such an action, if it were to occur, would hint at an underlying intention, a guiding intelligence, and a final destination that no one on Earth has any logical basis to fear. So, what would be the most intelligent opening move for a visitor from a distant star? And why does this specific date carry more weight than any of the speculation that has preceded it? Between the 18th and 24th of October, as 3I Atlas neared its critical rendezvous with the Sun, scientific teams across the planet mobilized, turning to every available stream of data in a quest for confirmation of its path. The primary obstacle was a matter of celestial mechanics. The comet's trajectory brought it so near to the Sun's blinding corona that it was effectively lost in the glare, rendering even the most powerful telescopes on Earth sightless. In this constrained window of observation, some pointed toward satellite imagery as a potential workaround, specifically making claims about data from the GOES-19 satellite. However, the truth behind using these images is far more intricate and requires careful, critical examination. GOES-19 is a geostationary weather satellite, an instrument fundamentally not designed for the rigors of deep space astronomy. Its main tools, the Advanced Baseline Imager and the Solar Ultraviolet Imager, are engineered with high precision to monitor terrestrial storm fronts and solar flares, not to detect faint objects from other star systems. The satellite's sensor plate scale and its overall sensitivity are inadequate for the task of isolating a magnitude 12 comet from the overwhelming brilliance of the Sun's background radiation. Despite these limitations, the idea of leveraging such data persisted, largely driven by the extreme difficulty of observing anything so close to the solar disk. For a credible analysis matching predicted positions, the ephemeris, to raw image frames, scientists must follow a meticulous and unforgiving process. Every image requires a timestamp with millisecond accuracy, a task that GOES-19 can perform due to its GPS synchronization. However, the truly monumental challenge is astrometric calibration. In contrast to dedicated astronomical cameras, the optics and field of view on GOES-19 are optimized for viewing Earth, not the starfields of deep space. To extract the position of a moving comet, analysts would have to align each frame against a known star catalog, correct for the satellite's own motion, and meticulously account for any optical distortions in the system. This step is exceptionally difficult, especially when the object of interest is many times fainter than the satellite's typical subjects. The analytical workflow would then proceed with differential tracking, a technique involving shifting and stacking multiple frames to reveal any object drifting against the seemingly static backdrop of stars. If a detection were even possible, its pixel coordinates would be compared to the predicted ephemeris, with every measurement assigned an error bar that transparently reflects the uncertainties in the process. A confident detection can only be claimed when the observed and predicted positions consistently align within these margins of error. In the case of 3I Atlas, no peer-reviewed study has confirmed a successful detection by GOES-19 during its solar conjunction. Instead, the most trustworthy trajectory data originates from ground-based and space telescopes from the period before the comet vanished behind the Sun. When it reappears in December, this same rigorous analytical process will be applied by instruments built for this very purpose, checking for any deviation from its forecasted path. Until that time, the scientific method demands prudence. Any claimed sighting must be supported by reproducible analysis, not just a visually suggestive overlay. This is how the astronomical community protects against falsehoods and ensures that if something genuinely extraordinary occurs, the evidence will withstand the most intense scrutiny. Rumors concerning 3I Atlas have proliferated online at a speed that rivals the object itself. Social media posts have alleged everything from clandestine engine burns to unseen course corrections, none of which have stood up to scientific verification. A recent formal statement from the International Astronomical Union's Minor Planet Center affirmed that there exists no confirmed evidence of anomalous behavior or any deviation from the predicted ephemeris for 3I Atlas prior to its perihelion. This has not, however, stemmed the flow of content on forums and in clickbait videos that circulate doctored images, alleged signatures of reverse thrusters, and dramatic overlays promising definitive proof of alien design. The reality of the situation is far less sensational and significantly more demanding. Detecting a magnitude 12 object like 3I Atlas near the sun's glare is a profound challenge even for seasoned professional astronomers. The majority of the viral claims depend on visual artifacts, such as camera sensor noise, cosmic rays striking the detector, or elementary projection errors. For instance, a widely distributed GOES-19 coronagraph video actually featured frames from a weather satellite ill-equipped for deep space targets. The supposed bright spot corresponding to the comet's position was identified as a hot pixel, a common sensor flaw, and not an interstellar visitor. The procedure for confirming a genuine engine burn or a change in trajectory is not as simple as drawing a line on a digital image. Scientists necessitate raw, time-stamped data that has been processed with meticulous astrometric calibration and a full error analysis. Each frame must be cross-referenced against a precise ephemeris, with uncertainties documented at every stage of the process. Even a slight deviation in the object's position has to be reconciled with measurement error, instrumental drift, and known non-gravitational forces like the outgassing of volatile materials from a comet's surface. As Dr. Anna Garcia from the European Southern Observatory stated, if you can't reproduce the result with independent data and a documented pipeline, it's not science, it's speculation. The vast majority of these online claims, estimated at around 95% by several survey teams, disintegrate under this level of rigorous examination. No peer-reviewed study, no official alert from the Minor Planet Center, and no NASA bulletin has substantiated any anomaly or abrupt maneuver by 3I Atlas as it approached perihelion. Until the object re-emerges from behind the sun and new high-precision astrometry becomes available, all discussion of engine burns or course changes firmly remains in the domain of rumor. The only thing currently moving faster than the comet is misinformation. For those hoping to discern a true sign of intelligent control, the best approach is to practice patience and maintain a healthy skepticism of anything that cannot be traced back to raw data and a published, transparent methodology.
Imagine a spacecraft hurtling past the sun at nearly 70 kilometers per second, a speed exceeding 200 times that of sound. At that precise moment, every single drop of fuel it expends delivers an outsized impact on its trajectory. This is the core principle of the Oberth effect, a concept that transforms a star's immense gravity well into a kind of cosmic amplifier for any object capable of firing its engines at the opportune instant. To understand how this works, consider a simple analogy. Think of a skateboarder rolling down a steep ramp. If they push off with their foot at the very bottom, where their speed is already at its peak, that push adds far more energy to their motion than the same push would on level ground. In the vacuum of space, the same principle holds, but the figures become astronomical. Kinetic energy, the energy of motion, increases with the square of the velocity. Consequently, when a spacecraft is moving at its fastest, each unit of propellant it burns contributes much more energy than it would if the craft were moving slowly. Near the Sun, the gravitational pull is immense. Objects like 3I Atlas are accelerated as they plunge inward, achieving their maximum velocity precisely at perihelion. If an onboard engine were to fire at that peak moment, the effect would be magnified. A burn of just 7 kilometers per second, a minor change compared to the comet's overall speed, could wrench its outbound path by tens of degrees, redirecting it toward an entirely new destination. That same burn, if executed far from the Sun's gravitational influence, would barely alter its course. This is not just a theoretical idea. The Oberth maneuver is a well-established and frequently used tool in space mission design. For example, NASA's Parker Solar Probe utilizes repeated close passes of the Sun to adjust its velocity and tighten its orbit, maximizing the efficiency of each engine burn or gravity assist. The underlying mathematics are straightforward but incredibly powerful. The energy gained from a burn is equivalent to the change in velocity multiplied by the object's current speed. At perihelion, with 3I Atlas moving at 68 kilometers per second, even a modest push translates into a monumental change in its kinetic energy. For a natural comet, the only source of thrust comes from outgassing jets, streams of vaporized ice, which are generally weak and poorly directed. But for a hypothetical, intelligently designed craft, this is the prime moment to act. The Sun's gravity effectively turns every kilogram of propellant into the maximum possible outbound velocity, making it the most efficient location in the entire solar system to execute a course change. This extreme efficiency is why astronomers pay such close attention to an object's behavior at perihelion. If 3I Atlas were under intelligent control, any deliberate change to its trajectory would almost certainly occur at this point. The resulting path would be dramatically different from what gravity alone would predict, and this discrepancy would become evident in precise post-perihelion measurements. Detecting such a shift is not simple, as astronomers must compare predicted and observed positions while accounting for every conceivable source of error. However, the physics of the maneuver would leave a clear signature, a sudden, sharp deviation in the outbound trajectory, far greater than anything that could be attributed to outgassing or solar tides. The Oberth effect turns the Sun into a lever, amplifying small efforts into major outcomes. For 3I Atlas, the moment of perihelion was more than just a close pass. It was a test of the laws that govern both natural and artificial travelers in the cosmos. Confirming a real maneuver by 3I Atlas is not a matter of dramatic skywatching or analyzing a viral video. It boils down to the dispassionate mathematics of astrometry. This scientific discipline involves measuring with arc-second precision exactly where the object appears against the backdrop of distant stars, and comparing those positions to the path that the laws of gravity alone would forecast. Every proposed engine burn or course correction would leave a distinct fingerprint in the sky. The comet's measured position would begin to diverge, frame by frame, from the trajectory calculated months prior. For scientists, the task is to detect this divergence early and to prove that it is a genuine deviation, not just instrumental noise or a measurement anomaly. However, the physics of the maneuver would leave a clear signature, a sudden, sharp deviation in the outbound trajectory, far greater than anything that could be attributed to outgassing or solar tides. The Oberth effect turns the Sun into a lever, amplifying small efforts into major outcomes. For 3I Atlas, the moment of perihelion was more than just a close pass. It was a test of the laws that govern both natural and artificial travelers in the cosmos. Confirming a real maneuver by 3I Atlas is not a matter of dramatic skywatching or analyzing a viral video. It boils down to the dispassionate mathematics of astrometry. This scientific discipline involves measuring with arc-second precision exactly where the object appears against the backdrop of distant stars, and comparing those positions to the path that the laws of gravity alone would forecast. Every proposed engine burn or course correction would leave a distinct fingerprint in the sky. The comet's measured position would begin to diverge, frame by frame, from the trajectory calculated months prior. For scientists, the task is to detect this divergence early and to prove that it is a genuine deviation, not just instrumental noise or a measurement anomaly. For the Oberth effect, the Sun turns the comet into a lever, amplifying small efforts into major outcomes. For 3I Atlas, the moment of perihelion was more than just a close pass. It was a test of the laws that govern both natural and artificial travelers in the cosmos.
The crucial metric in this endeavor is called delta V, which represents the change in velocity an object undergoes, measured in kilometers per second. At perihelion, even a relatively small delta V of, for instance, 1 kilometer per second would be sufficient to alter the outbound path of 3I Atlas by tens of thousands of kilometers over several months. To put this in observational terms, a 1 kilometer per second burn at perihelion would produce a separation on the skyplane of approximately 20 arcseconds by the time 3I Atlas approaches Jupiter in March 2026. To be certain of detecting such a shift, telescopes must achieve a positional accuracy better than 5 arcseconds, and ideally much higher. For more significant burns, the divergence becomes more pronounced and easier to measure. A 3 km per second maneuver would generate a gap of over an arc-minute, while a 7 km per second burn would pull the comet several arc-minutes away from its natural course. These are substantial differences that even mid-sized observatories or spacecraft with decent optics could measure with high confidence. The process is rigorously methodical. Each observation is time-stamped to the second. Its field of view is calibrated against a star catalog like Gaia DR3, and every position measurement is checked for systematic errors. Measurements are repeated over days and weeks, creating a chain of data points that will either closely follow the predicted ephemeris or begin to drift away. If this drift consistently surpasses the measurement error, if the observed positions move away from the predicted track by more than the calculated uncertainty envelope, the case for a real artificial maneuver grows stronger. To ensure these judgments are transparent, astronomers publish what are known as sensitivity tables. These tables list, for each potential burn size, the minimum expected separation on the sky, the required measurement precision, and the frequency of observations needed to detect the divergence early. For 3I Atlas, the consensus is clear. A 1 km per second burn is detectable if positions can be measured to within 5 arcseconds every few days. For larger burns, the standard is even less stringent. This is the yardstick by which all claims of engine burns and course changes will be evaluated when the comet reemerges from behind the sun. The conclusion is straightforward. If 3I Atlas did fire its engines at perihelion, the evidence will not be a blurry streak or a viral overlay. It will be a cold, precise, and reproducible shift in the sky, tracked across dozens of independent measurements and confirmed by the world's most reliable astrometric pipelines. Anything short of this standard remains speculation. Despite its appeal in science fiction, Earth is a strategically poor choice for any incoming interstellar visitor seeking to establish a presence. The planet's deep gravity well necessitates an enormous amount of energy for landing, launching, or even achieving a stable orbit. No probe, whether of alien origin or otherwise, would squander its precious fuel reserves by dropping directly into such a high-gravity environment, particularly when more accessible targets are plentiful. Added to this physical challenge is the complex reality of human society. With a population of over 8 billion people, a mosaic of military forces, extensive surveillance networks, and established planetary defense protocols, any abrupt arrival would undoubtedly trigger a global response, not a quiet reception. As Dr. Marcus Lee from the Planetary Defense Coordination Office stated, Earth is the last place you'd want to make a surprise entrance. Recent mission data validates this assessment. 3I Atlas already passed by Mars earlier this month, coming within 28 million kilometers without any indication of deceleration or an attempt to land. If the object's objective were to target planets for contact or colonization, Mars, being uninhabited, rich in resources, and effectively undefended, would have presented a far more logical initial step. Instead, its trajectory remained unaltered, a silent flyby that strongly undermines the notion that Earth is its next destination. From a strategic viewpoint, bypassing Earth is the most sensible course of action. Any advanced intelligence would recognize the risks associated with provoking a planetary-scale immune response. The logical move is to avoid such drama and aim for a location that is easier to access, less defended, and abundant in resources. This reasoning shifts the focus to the outer solar system, where the strategic considerations and opportunities are vastly different. Jupiter emerges as the next major milestone for anyone tracking 3I Atlas. If an intelligent maneuver was executed at Perihelion, the object would be on a course to sweep past Jupiter's orbit on March 16, 2026, closing to within 54 million kilometers. For mission planners, this represents a prime rendezvous point, a window where the trajectory, whether natural or artificial, will be tested against every scientific prediction. The logic of a Jupiter playbook is compelling. Ganymede, the largest moon in the solar system, offers water ice, a protective magnetic field, and gravity that is only a fraction of Earth's. These are the essential ingredients for life support, rocket fuel production, and the kind of base construction that avoids the risks of a deep gravity well. Callisto, located farther from Jupiter's intense radiation belts, offers another safe harbor. Both moons are rich in resources and free from human presence. The idea of digging under kilometers of ice for protection is a practical engineering solution for any advanced traveler. The inbound trajectory of 3I Atlas has also led to speculation about its origin. Barnard's star, just 6 light-years away, is situated in the same general area of the sky as the object's approach vector. The journey would have taken tens of thousands of years, and while no direct link can be proven, the coincidence keeps the question alive. For those observing, the probability that 3I Atlas is anything other than a natural comet remains exceedingly small, roughly 1 in 1,000 by the most generous estimates. Nevertheless, the next checkpoint is clear. As the object re-emerges from the sun's glare in mid to late November, telescopes will be trained to detect any sign of a course change. The countdown is on, and the world's astronomers are prepared to see what, if anything, deviates from the expected pattern.